Kalispera, dear friends and colleagues. It is a great pleasure to welcome you all here today, both those of you who are here, but also those who are connecting remotely. I would particularly like to thank Professor Françoise Combs and thanking her for delivering this year's lecture, which has the title of When Black Holes Impact Galaxies. Let me just say a few words about the Kylafis lecture series. The Foundation for Research and Technology and the Institute of Astrophysics have established this lecture series to honor Professor Nikos Kylafis for his instrumental contributions and continuing commitment towards development of astrophysics research in Crete and in Greece more generally. Nikos was truly a driving force behind the creation of FORT's Institute of Astrophysics a few years ago. This process, some of you may know, was not at all linear. It was ambitious, and eventually it came to fruition, thanks to Nikos' efforts and perseverance, which helped decisively towards bringing this effort to a successful conclusion. From the very beginning, special emphasis was placed in establishing the new institute based on the same principles and terms of excellence that all FORTH institutes and activities abide to, aiming to foster and facilitate the pursuit of excellence. FORTH has undertook several concrete initiatives, including the now long tradition of the Onassis lecture series, which attracts outstanding scientists from all over the world. Actually, it's a very nice coincidence that this year's Onassis lectures have been dedicated to a related topic of astrophysics, that of gravitational waves, where black holes play a pivotal role, I think. So we are really looking forward to the next episode of this great saga. Now, this is, of course, not the end. In addition to all these initiatives, we have established more tools to foster interactions and communication between different institutes. For example, the intramural FORTH Synergy Grants, as well as the FORTH Research Excellence Award that was given this year in our biannual gathering together. Now, the Kylafis lecture is coming as a worthy addition in this roster of focused activities. With this opportunity, I would also like to congratulate the Institute of Astrophysics and especially Director Vasilis Harmandaris for maintaining this course and organizing today's lecture for the 4th time. Thank you all again for being here today. And we are all looking forward to hearing about the recent and exciting developments about black holes from Professor Combs. Thank you.
Θα συνεχίσουμε με το Διευθυντή του Ινστιτούτου Αστροφυσικής του ΙΤΕ, καθηγητή Βασίλη Χαρμαντάρη.
Καλησπέρα και από μένα. Dear colleagues and students, ladies and gentlemen, it's also a great pleasure to welcome you all to the 4th annual Nick Kylafis lecture for 2022. Before I introduce our distinguished lecturer, Professor Françoise Combs, I would like to say a few words about Nick Kylafis, the reason why we are here all today. The person who, as it was mentioned earlier, was instrumental for the establishment of an active, internationally recognized astrophysics group in Crete, at the University of Crete, as well as at the Foundation of Research and Technology, and a person whose actions and endless energy convinced the Greek government to found the Institute of Astrophysics back in 2018. This is more relevant to the younger people in the audience, since the senior ones, I'm sure, do know of Nick and his influence on the academic ecosystem of the University of Crete and FORTH. Nick Kylafis received his bachelor's degree in physics from the University of Patras and his PhD in theoretical astrophysics from the University of Illinois at Urbana-Champaign back in 1978. After postdoctoral fellowships at Caltech and the Institute of Advanced Study in Princeton, he joined the faculty of Columbia University as an assistant professor in 1984. However, the beauty of the island of Crete and the opportunities of the newly founded University of Crete and the research center, which later became FORTH, made him leave the Big Apple and came back to Greece in 1985. Nick moved quickly through the ranks of the physics department, becoming full professor in 1997. And he also served in a number of administrative positions, including the position of the chairman of the physics department, dean of the School of Sciences, as well as member of the council of the University of Crete. For his research, Nick has been contributing to various areas of theoretical astrophysics with special interest in production and transfer of radiation, with applications in spiral galaxies, compact X-ray sources, and astrophysical measures. In fact, one of his early works was the so-called Goldreich-Kylafis effect. Even though in physics, we do know that time only moves forward, somehow it seems that for Nick, time seems to be standing still, in particular since he formally retired and became emeritus professor in 2016. And somehow he is managing to be even more productive than before, both scientifically as well as in service. So in 2018, he was elected member of the Council of the European Astronomical Society. And in 2019, he was awarded the Pichoridis Award for Excellence in Academic Teaching by the University of Crete. So in 2019, when the Institute of Astrophysics formally commenced its operations, and on the occasion of his 70th birthday, it was only natural to establish the Nick Kylafis Lecture in his honor. This was the least we could do for his 35 years of scientific contributions and leadership towards the founding and continuous improvement of the astrophysics group at the University of Crete and Forth. Under the auspices of the lectureship, one distinguished theoretical astrophysicist is invited annually at Forth for a brief visit. Professor Françoise Combe, Chair of Galaxies and Cosmology at the Collège de France and distinguished astrophysicist at Paris Observatory, is our 2022 lecturer. Professor Combe is internationally recognized for her seminal discoveries in theoretical astrophysics and cosmology, in particular for mechanisms associated with galaxy evolution and dynamics, the creation and feeding of supermassive black holes in galactic nuclei, and the properties of dark matter. She is an impressive scientist with great physical intuition and a unique ability to develop the theory, write the code to do the numerical calculations, as well as obtain and reduce and analyze the data which will test the theoretical predictions, and all of the above with an amazing efficiency. She is one of the most prolific astrophysicists in the world, having published over 600 papers in peer-reviewed journals, which have received over 41,000 citations. Professor Combe has also authored several books, and she is offering her time in various administrative positions and scientific committees in France and international organizations and astrophysics journals. She has supervised more than 24 PhD students, among which is the current president of Paris Observatory, and even more postdocs. Being one of these postdocs 25 years ago was an extremely formative as well as humbling experience. In addition, Professor Combe has received a number of highly prestigious awards, including the L'Oréal UNESCO International Prize for Women in Science in 2021. She is a Legacy Fellow of the American Astronomical Society in 2021. She received the prestigious Gold Medal of CNRS in 2020. She is Commander of the Order of National Merit of the French Republic. She received the prize of Jules Janssen in 2017, the Tycho Brahe Prize of the European Astronomical Society. This is the most prestigious prize in 2009. And she is also an officer of the Légion d'honneur of the French Republic. She is also a member of several prestigious academies, such as the Académie des Sciences in France, Academia Europaea, and others. Today, Professor Combe will talk to us about supermassive black holes at the centers of galaxies and how their presence influenced their evolution. So at this point, I would like to ask Professor Combe to come to the podium to receive the award for the lecture by the president of Forth, as well as a few gifts. Thank you.
Hello, so I'm very happy to be there. I'm in honor of Nick Kylafis, very honor also. So I will speak today about this, but I have to stop there. Yeah. About black holes in galaxies. And as an introduction, I want to recall that we have learned a lot in the recent years. For instance, in 2019, we have seen for the first time the first shadow of a black hole. So you see in the left, this orange ring that you might have seen already, which is, of course, you don't see the black hole because the light cannot get out of the black hole, but you see the gas which is rotating around. And it's the resolution here, it's really a challenge because this Event Horizon Telescope had about 20 micro arcsecond resolution. It was obtained by this kind of combination of a lot of radio telescopes in the world, in Europe, the Pico Veleta Triron, in South America, Japan, in North America, and so on. And so that they can make interferometry with a baseline of 12,000 kilometers. And that's why you see that the size of the ring here is 1 light week. So why we call this black spot that you have inside the shadow of the black hole, because in fact there is a lot of photons that goes in this region, but they are all swallowed by the black hole. So it's really a shadow. And there is it's a very, the shadow of the black hole has a ring which is about 2.5 the horizon. So we have an idea of the horizon and we have an idea of the mass of the black hole, which is 6 billions of solar mass. And of course, this Event Horizon Telescope worked at 1.3 millimeter. It's a first breakthrough because in the past, in the last decades, we had some other VLBI, very large baseline interferometry, but with centimeter wavelength, and centimeter, the atmosphere is very transparent, coherent, there is no perturbation. That's why it's easy. So you see it was done in M87, which is at the center of the Virgo galaxy, Virgo cluster of galaxies. And you have 4,000 light years, you have 2,000 light years, you have 0.1 light years here. And finally, a light week. So you have a multi-scale, and that was recalled in this image. The Virgo cluster there at the right, and you have this jet, and we will speak about jets in this presentation. You have the jet, which has a very bizarre shape because it has some collision with the gas in intracluster gas. Then if you make a zoom, you see 80,000 light years. You make a zoom to see the jet is starting very straight at 2,000 light years, and then you see at 60 light years how you have a jet which is splitting in 2 parts, like a cone here. And after that, you have finally the shadow of the black hole given by the Event Horizon Telescope. The mass of the black hole is 6 billions, as I just told you. So now we can have why they have been, for this first image, chosen M87, which is very far from us. It is 2,000 times further from us than the black hole, which is in our own galaxy, the Milky Way. The Milky Way has a black hole in the center. It's called Sagittarius A star because it is in Sagittarius constellation. But the coincidence is that although this M87 is 2,000 times further, it has a mass of a black hole 2,000 times larger than the black hole which is in our own galaxy, which is 4 million solar mass only. So finally, when you look at these two, the angular size is the same. It's a coincidence, but it's the same. So they could have done this, and in fact, they have tried. The big problem is that, as you see, the Horizon telescope, the Horizon radius, sorry, is proportional to the mass. That's why you have this coincidence. But also the period T is proportional to the mass. So when you look at the gas circling around the M87 black hole, it does this in 2 months period. So when you try to take the picture with all these telescopes in the world, then you have about a quarter of an hour to calibrate your telescope and so on. And in the meantime, the gas around Sagittarius A star has gone because it has been swallowed by the black hole. It has a period of 30 minutes only. So that's why you have not seen the black hole of our own galaxy. And just, I recall the Nobel Prize in Physics in 2020, which was given to the 2 discoverers of the black hole in the center of the galaxy, Rainer Genzel and Rages, and also to Penrose. Why? Because Penrose has been the first to convince astronomers that black hole exists. In fact, even Einstein in the early 20th century was not convinced that you could make a black hole out of the explosion of a supernovae with a high mass, because every people was thinking that although Schwarzschild had made a solution of the Einstein equations, it was symmetric, only a point source, and it is not physical. So as soon as a supernovae will explode, it will go in every direction. There will be no remnant. And only, even with a rotation, Kerr has a rotation solution in 1963 of the black hole equations, and it was rotating, but very symmetric. So only Penrose, with a very clever solution with changing the topology, said that with the Einstein equation, you have ineluctably black holes existing. So this is why this is a breakthrough. So now you have seen that in the spring of this year, in 2022, also the Sagittarius A star has about the same kind of image. Of course, is very difficult because you have to stack several periods of the flare of the black hole, and you have 3 points. We are not sure that the 3 points are completely, it's on not only one period, it's several periods. So it's more difficult. That's why they have taken 5 years to finally give this image. And these are the real image, but you see that there are still a lot not very neat. And here are simulation that what we could get after some other progress in the resolution, when you have, for instance, a telescope in space, we can be 300,000 kilometers from us, we'll have some kind of resolution like this, and we will see also the jet coming out of the accretion disk on the black hole. This is very interesting to know how jets are formed, and although we have theory, but we have not yet. And I want to mention also a breakthrough done by gravity in 2018 out of the black hole of our own galaxy, Sagittarius A star. And even before the image that was done by Event Horizon Telescope this year, 4 years before, they got this gas rotating around the black hole with the same 10-20 microarc seconds. So although you have only the VLT, Very Large Telescope at ESO, which at most 100 meters, since the wavelength is very small, then they can have about the same resolution that the Event Horizon Telescope. And they have seen this, which is almost face on, not edge-on, while the galaxy is edge-on, even before the Event Horizon Telescope. So it's a gravity at the VLT. Now, what we will learn about the black hole, about these images, if we can have also the photon ring inside the ring of the gas, which is rotating around the black hole, you could have a ring of photons, which are forced to rotate also around the black hole. And all this will give you the spin of the black hole. We want to know how much it is spinning. As you see in this picture, while we have a zero rotation or the maximum rotation of the black hole, then the size of the ring of gas will decrease if the black hole is spinning, or if it is spinning in the retrograde sense, it will increase. So the measuring the size of the gas ring with precision and the photon ring will give you the spin of the black hole. So in the future, for now, we know that it is spinning, but we don't know exactly the precise value. Now, I want also to speak about quasars. That my theme here is to tell you that the black hole in galaxies are impacting the galaxy host. And so what are the quasars? In fact, these quasars, or active nuclei, have been discovered by Martin Schmidt in 1963. And how he did that, in fact, you know, there was radio sources, a lot of radio sources without any distance, because there is no lines and no redshift. And when people tried to find optical counterparts to this radio source, they found that, which looks like a star. Bright star, you have diffraction patterns here, it's a point source, so they call it quasar or quasi-star. They didn't know what it is, but when they make the spectrum, it was a very bizarre spectrum. And the idea of Martin Schmidt said, well, if you redshift by a large amount, and at this epoch, a large amount was a redshift of 0.15. Now we have with James Webb Telescope redshift of 10 to 20. So it's ridiculous, but at this epoch, it was a very huge redshift, 2 billion light years away. And then you can recognize that it is a galaxy spectrum. And that's why he discovered that the quasars are the nuclei of galaxies. And why we did not see the galaxy is because the quasar can radiate 10 to the 3, so 1,000 times more than all the stars, the 200 billion stars that there is in the galaxy. So you see it's very, very energetic, so that you cannot see the galaxy. And only with the Hubble Space Telescope, where you have a telescope outside the atmosphere that did not perturb by the seeing the images, you can subtract the point size here image, and then if you subtract, you see the galaxy behind, which is there after subtraction. So indeed, all the quasar and all active galaxy are a black hole, supermassive black hole in the nucleus. And we know now that even if the galaxy is not active, there will be a supermassive black hole in each center of each galaxy. So since I want also to show you the feedback, so feedback is also mostly due to jets. When the black holes eject a lot of matter, here you see that the quasar that you've seen before, 3C273, has a jet that you see with the Hubble Space Telescope, HST. You see in Chandra, which is X-ray, the satellite in X-ray, and you see the Merlin, which is interferometer in radio. So at all wavelengths, you see a jet, which are a plasma, ionized gas, proton, electron, which are moving at relativistic speed, almost c. And since you've seen that this jet is made of clumps, in fact, it's not regular. You have intermittent ejection, and you have this kind of things here. The idea was, well, maybe we can measure the proper motion of these jets to know the velocity. And indeed, what you see at the right here is several pictures of a jet at 1919 or 2000, 2001, so a few years. And you see these clumps moving. And what the results was is that, by surprise, in fact, the velocity is much larger than the velocity of light that we call superluminor. You see here, for instance, the 3C279. They are going by 60 light years in about 6 years. So it's about 10 c, the velocity, the proper motion that you deduce. And why? In fact, it was a mystery for a while, but it's a very simple explanation. Of course, it's an illusion, but the illusion comes from the fact that from 2 points, for instance, A, the fixed point, and B, which is moving here, you have a motion which is almost c, relativistic. But the messenger the photons that B sends to the telescope or A sends to the telescope are also at the velocity c, of course. So there's a competition between these two velocities, and this is very important that B is closer to the telescope. And since it is closer, it has less path to run, and it appears to go very fast. It's only that. So if you compute the time it takes to go to A to B here by x, so the apparent time is the real time minus x over c. And if you develop all this, and for this you have to have a theta, the angle that the jet is coming towards you, very small. And then you can show that indeed, if beta, which is v over c equal 1 and cos theta equal 1, you can have a large factor, 10c or so. But of course, at the beginning, the radio astronomers see all these radio sources, they were all ultraluminous. Why? Because in fact, they saw only the most bright sources, and the bright sources are boosted when they are coming towards you. So we are seeing only these sources, and they were all ultraluminous. Now, we see in the nearby universe a lot of active nuclei that are not as strong as quasar. We call it Seyfert galaxies. And sometimes there are type 1 and type 2, the very big classification. Type 1 is galaxies where you see a broad line region, that is gas rotating around the black hole with a high velocity. What we see in the image around the black hole was 100,000 kilometers per second. So it's a c over 3. So here you have very, very high velocity in the broad line region because of the rotation. And then you have narrow line region farther from the black hole. And in type 1, you see both. the broad line region and the narrow. But for type 2, we don't see that. So the explanation to see that all active nuclei are the same beasts, but we see them differently, is to suppose the existence of an obscuring torus thick enough that you have exactly the kind of ratio between the number of type 1 and the number of type 2. So you have to be very obscuring. And if you see the active nucleus from this side, you will see only the narrow line, but not the broad line region. Okay? So this is the current paradigm to explain the classification of all active nuclei in type 1 and type 2. But I will show you now that with the recent work that all people are doing with ALMA and with the VLTI, we have another view, in fact. And the view is more like this. It is around the accretion disk that you have here in the big blue bump here in the black hole, around the black hole, the broad line region. Then you have a dust which is have a ring of sublimation, because of course, if you are too close to the black hole, the dust will be volatilized and does not remain there. And after a certain radius, you can have dust. So we call it the sublimation radius of dust. And from this radius of sublimation, you have ejection of the dust and gas by the black hole because of this feedback. And you have like a hollow polar cone that have a lot of dust. And in addition, we measure with ALMA and other molecules the thin disk. So finally, the paradigm of very thick disk torus is not there anymore. We have a thin torus. In general, the torus is cold, so we see it in molecules, but we see better in the dust the polar region. So I will show some kind of things. So I will separate my demonstration in 3 parts. I will first show you what we have learned recently about the feeding of the black hole, how the black hole eats the gas. In fact, it's very difficult to provide gas. Why? Because the gas is rotating around the black hole and you have angular momentum, and this angular momentum is conserved. So you have to exchange angular momentum. For that, you have to exert gravity torques. And for that, you need non-axisymmetric things like bars, spiral, and so on. So I will explain that. And then also I will explain that why we have observed a lot of molecular outflows in the last decade, which means that a lot of gas is deprived from the host galaxy and cannot form stars. And then I will describe the molecular theory that we have observed. So first, the Bard galaxies. So even the Greek team, Kontopoulos et al. From Athens, have done a nice work to describe the orbits, periodic orbits in a bar potential. And here you have a picture, a cartoon of their results here. It's when you have a bar which is parallel to the x-axis, horizontal axis, you have orbits of the stars which are mainly parallel to the bar. And then at each resonance means resonance of particle motion with the bar potential. The bar potential is rotating like a solid body. So when you have a resonance, which are called first the inner Lindblad resonance and co-rotation, then outer Lindblad resonance, you change by 90 degrees this orientation. So you have parallel, perpendicular, parallel, and so on. And this is for stars, because stars don't collide with each other. They are collisionless medium. But when you have gas, then clouds of gas collide and they cannot cross each other. So you cannot have perpendicular orbits. What you have is this kind of ellipses which precess at a precession rate, which is a function of omega, the rotation rate, and the kappa, the cyclic frequency. And then you see that progressively, because of dissipation and collision, they are changing by 90 degrees, but gradually and not suddenly. And then you form a spiral structure. And this spiral structure, of course, makes a different phase between the bar and the gas, and there is torques. But then, when you arrive at resonance, you have the phase is completely in phase, the gas and stars, and then you stop. And you see in the top right, this typical image of a Bard galaxy seen in color, P minus V, and you see that there are rings. One is a nuclear ring, one is a co-rotation ring, and one is the outer resonance ring. And these, why is it blue? That's a very blue, because the gas is piling there. and making stars. That's why. So we know that the gas will be piling up here in the resonances, and this is a problem to fuel the nucleus. Here we have, as a function of radius, you see the frequencies. When you have the rotation curve of a galaxy, you have the frequency omega, which is V over R, omega, and kappa is also a derivative, second derivative of omega. So when you have V of R measured, you can have all this frequency, and omega minus kappa over 2 is very interesting because it's a precessing rate of all these elliptical orbits of the gas that I've shown. So when you have omega p, the horizontal pattern speed, which is constant as a function of radius, then when it crosses this, you have two inner resonance, you have a co-rotation, and you have an outer resonance. So why you will be able to bring gas to the center? It is because you can have a decomposition of nuclear bar inside the primary bars. And why? Because inside the two resonance, you begin to be perpendicular to the bar and you don't sustain the bar anymore. So it's weakening the bar. You can also weaken the bar because there is a vertical resonance that you see in a bulge forming like a peanut-shaped bulge. And then all this means that you will be able to decouple a secondary bar that you see in a simulation, for instance, by Friedrich here. You have a primary bar and a secondary bar. And in the gas, you have also this ring. So this embedded bar will prolong the action of the primary bar and will fuel the center of the galaxy. And to know what are the signs of the torques, that is the gas going toward the center or outwards, you have this little cartoon here. The bar is splitting the plane in 4 quadrants. When you are in the red-pink quadrants, you see that the tangential force that makes the torques are restoring towards the bar, which is parallel to the horizontal axis. And you see that the torque is positive, same signs of omega here. So all the gas outside co-rotation will go to the outer resonance. While if you look at the prolongation of this power structure inside the bar, you have this characteristic dust lane which are along the bar. And then you are in the other quadrants, it is negative, and all the gas from co-rotation inside will go to the center. Okay, so now we can quantify this. We know the principle, but we can have figures. For instance, a galaxy like NGC 3627, you can have the potential. How? We know that the potential inside is due to the old stars. The dark matter is negligible inside the 1 or 2 kiloparsec in the center, and the gas is also negligible. So you take a rad image, which is a tracer of old stars, and in each pixel, you have the density, and by a Poisson equation, you have the forces, potential and forces. Okay, so each pixel, you can have the force, and you can have the quadrants here. The red is positive torque and blue negative torque. And then if you make the gas map with an interferometer, here it was a NOEMA interferometer, the contours are the gas distribution. You see that the gas is distributed in the blue quadrant, so the torque is negative. And then if you average out on azimuth, you have this figure here, which is the relative loss of angular momentum, dl over L, in one rotation, and you see that it's about 30%. So this means in 3 rotations, the gas will be driven toward the center and fuel the adjuvant. So this is a first step to know if you are feeding or not. And we did this kind of statistic about 20 galaxies, but with the IRAM interferometer. That was at the epoch 6 antennae. Now we have 12 antennae. It's called NOEMA. But about 20 galaxies were observed with this interferometer. And we conclude that only 30%, 1/3 of the galaxies, were in the case where there was a negative torque, that they were fueled at the scale of 100 parsec. So what is the conclusion of this? Is that in fact, the galaxy, well, all these galaxies were Cepheid, so were active, but they spent only 1/3 of their time in the fueling process at 100 parsec scale. That's only what we can conclude. And why, in fact, it is because, for instance, in 6951, you have a zoom on the center. You see that there is a bar, there is a ring, and if you make a zoom, you see that the gas is stalled in the ring and cannot go to the center. So you need to wait that a nuclear bar will decouple, and you see a simulation in the right top, a 3 snapshot with a zoom in the right part, and you see at the beginning there is a big accumulation of gas in the ring, and progressively there is nuclear bar decoupling, and all the gas is going further to a ring which is the ring of the nuclear bar. So embedded bars can help to have the gas to the center. So now we wanted to have more resolution, so to go with the ALMA interferometer, which can give you 10 times more resolution. So for instance, this is a bar galaxy, 1433. You see a ring here with the HST, the Hubble Space Telescope, in blue, which is star formation. And then in the zoom, you have in orange the map of the molecular gas in CO 30322, that finally you see a second ring. And this is certainly because there is 2 resonances here, and we could have expected the second ring, and then we see that. So finally, there is no fueling in this galaxy, but we saw also a little in the minor axis, so in the perpendicular direction, we saw a little outflow. It is a very small outflow, but at least there is a feedback. So that could explain maybe why we have not seen any inflow. So you see the torque in one rotation, it's always positive. And inside, we have an outflow, which is preventing us to know what is happening. But here you see that we have not only a big ring, but a second ring. So this was an unsuccessful fueling mechanism. But for the second, it was more positive, and it was really surprising, because in NGC 1566, you have these big bar galaxies, a spiral structure, and inside, again, you have this ring at the inner Lindblad resonance. And you see in red the field of view of ALMA at this CO322 line, which is 18 arcsecond. And what we see in the border of the field of view, we see the big ring, and inside we have a nuclear disk. And the surprise is that the nuclear disk has a small nuclear spiral that you see there. And the widening sense is trailing, making that with respect to the rotation, the sense of the galaxy, the mass enters the concave side of the spiral. And it is exactly the same trailing structure than here. And why we were surprised to see this trailing structure? It is because we were expecting a leading one. A leading one, why? I just recall you the orbits that were done by the Kontopoulos group here. You have parallel orbits, and then now we are in the reference frame of the bar, rotating with the bar. So at co-rotation, you are just making a small epicycle. And then you see here at the top right that we have the rotation curve, V of R, and this precessing rate, omega minus kappa over 2, which is the precessing rate of these small ellipses. And you have both the maximum go down, and then when you are close to the black hole, you have a Keplerian potential. So all frequencies come up, the velocity and omega and everything comes up. And that's why we can exchange the sense of rotation of this spiral. So here you define the stellar orbits, which are periodic, and just I put some colors to best the scene. If you have the gas streams, it will be gradually changing by 90 degrees, and it is some trailing in the outer parts, but in the inner parts, what you are expecting is this. So first in blue, the trailing, and in red, you have the leading. Why? Because you know this omega minus kappa over 2 is increasing when the gas is going to the center. So this is trailing, and then it is decreasing. So you should expect this without any black hole. If you have a black hole, then this precessing rate is again increasing, and you will have a trailing, okay? I just make a little animation so that to make this more easy to understand. When it is coming up, of course, the precessing rate is increasing. You have a trailing, okay? And when it's going down, it is a reverse. It goes in the reverse sense. You have the leading. And if you are inside the sphere of influence of the black hole, very nearby the center, it's coming up again. So again, you have a trailing. Okay, this is very simple and geometric. And we are, in fact, with ALMA, we are in the 25, 30 parsec size where the black hole potential is dominating. So that's we are finding the trailing spiral structure. And this is why we have talks that are the other sense. So we now have proven that we are fueling the active nucleus. So this is exactly what we have here. We have this kind of picture, and when we compute the torques by the 4 quadrants, the blue being negative, the red positive, okay, you see that the gas, the spiral structure, the trailing spiral structure is in the blue zone. So you have exactly negative loss of angular momentum. So the amplitude is very large, is 50%. So in 2 rotations, the gas will go to the center very quickly. So we understand the feeding. And this kind of nuclear spiral that it was not possible to see it with another resolution than ALMA. We see in many galaxies, for instance, the NGC 1808, you see at 10 parsec scale, this very nice nuclear spiral with CO322. We see it also in HCN 423, HCO plus 423, which are the dense tracers of the gas. So it's not only a small amount of gas, very dense gas. And also in this galaxy 613, I want to insist that when you have, even with ALMA, when you have not enough resolution, and this was the case by Miyamoto et al. At the beginning, if you don't push ALMA to the highest resolution, you find the ring, but you don't find the nuclear spiral that we find here. So the resolution here was 0.06, so 5 parsec resolution to see this nuclear ring. And another point is there, you see the velocity. Here you have 10 arcsecond in the box, and you have the velocity, red and blue, are about the major axis, or about east-west. But when you make a zoom here by a factor 10, you have 1 arcsecond now. You see the contours are the nuclear spiral, the S of the nuclear spiral, and inside you have this molecular torus that I will describe more. Here you have the continuum in synchrotron, and in HCO plus you have this exactly the same scale. And you see that the PA now, the major axis, is vertical. You have the red and blue, which are in the north-south. So it's completely, you see already that you will have a molecular torus which is not aligned with the rest of the galaxy. And why they are not aligned? In fact, we think that they are precessing, maybe due to at lower than 1 parsec, you can have this precessing due to the black hole spin, which is dragging the referential frame here. So either, we don't know exactly, either this gas is viscous enough to have a warp in between the 2 planes, 2 orientation, or if it is not viscous enough, you can have a break and you can have some rings, sub-rings, which are not at the same orientation as the main one. And in fact, it is exactly what we saw, for instance, when you have VLBI and we saw water masers here in NGC 4258, you see that indeed the accretion disk is warped, and it is due certainly to that also. So in this galaxy again, we can compute the torques here about the gas inside the big ring, and indeed it is negative. So we still prove that the active nucleus is really fueled. Now I will just go to the feedback now. Do we see a lot of molecular outflows? Yes. And especially on the same galaxy here, if you go to the minor axis, you see these black contours, which are the VLA contours, the synchrotron radio jet. And in this direction, you see in the molecules a blue wing and a red wing. That is really an outflow exactly in the same direction. You see it in the velocity major axis position angle here. And you have a high velocity that you don't resolve, in fact. You have an outflow which is not resolved. It is at a velocity of 300 kilometers per second. So you have both the fueling in the plane, and then in the perpendicular direction, you have an outflow, molecular outflow. So feeding and feedback are occurring simultaneously. In 1808, we have seen that we are fueling because there is a nuclear spiral, but at a small scale, there is no molecular outflow. Why? it was a surprise also because this galaxy is well known for a long time to have large winds, but at large scale, 100 parsec. And if you have resolution, you can see that at small scale, there is no molecular outflow. So we conclude that it is a feedback due to the starburst, in fact, to the supernovae feedback. So if you have not enough resolution, you cannot distinguish between the AGN feedback and the star formation feedback. And here you can. Okay, so in the AGN feedback, there is a lot of work now that has been done for many nuclei, active nuclei. And we think that there is two modes to eject gas. Either you have a quasar, a very powerful active nucleus, and then it is so active that it is at the maximum of luminosity, Eddington luminosity, and then the radiation pressure pushes the gas. So we have a wind, which is not collimated, but a very big wind. And for all the Cephers that I've shown you for the moment, we are not in this case because we are very low luminosity, lower than 1% of Eddington luminosity. So the radiation pressure is not enough. However, we always have a radio jet, and the radio jets can, these relativistic particles can drag some molecular gas and have this feedback anyhow. This is a case, for instance, of NGC 1068, where you see again at large scale this bar and the ring in the center, which is the resonance inner Lindblad resonance ring. And we have also in the black contours here a radio jet, which is known for a long time, which is 1 or 2 kiloparsec in size. And we see also a molecular outflow, which is rather high, 63 solar mass per year, 10 times the star formation rate. So it has really a large efficiency to stop star formation after a while. And we interpret that because the AGN is pushing, the jet is not perpendicular to the disk, but it's pushing the molecules which are in the disk. And this is due to the fact that the accretion disk has not the same orientation as the main disk of the galaxy. That's why there is more coupling between the jet, which is perpendicular to the accretion disk, and which is pushing the gas in the disk. And here we see clearly inside the ring, we see a nuclear disk again. And in CO625, again, more resolution. We have now a molecular torus, which is 3.5 parsec. And perpendicular to it, we see the contours of the continuum at this frequency. And the continuum at this frequency is the dust. So you see the dust is perpendicular. While even in CO221, you see the torus, which is rather perpendicular to the, oops, yes. So here you see a very nice picture made with the sphere in near infrared with the VLT here. And it is a polarized image, and the difference with the central symmetric. So it puts in evidence all this polar structure that I described in my change of paradigm. You see in the dust, all this polar cone here, and the molecular torus is perpendicular to that. So it fits very well with the image that we have. The molecular torus quite thin and a polar cone again. And this is seen now in many galaxies like this. You see in the green the jet structure, the perpendicular to the disk, and you see that the continuum of the polar dust, the dust is polar and not in a torus, which is a perpendicular structure. So why we see mostly the polar, because the dust here ejected by the AGN is hotter than what it is accreting in the disk. So we see in the dust essentially the perpendicular structure, and in the molecules the aligned equatorial structure. So as for velocities, we have found a lot of molecular outflows. I've just already shown one, but this one is very peculiar. Why? Because it is very, very collimated. You see several images of ALMA. You have in grayscale the CO line, which is in the center velocity, normal CO line, and the wings with blue wings and red wings, so the approaching and receiving, are seen in contours, and you see that they are quite collimated. When you increase the resolution, it's really like a pencil beam. And what is also remarkable, it begins blue and red, and it finishes red and blue. So it's changed sign with respect to the velocity to the observer. And why? Because it is precessing again. So it is a jet which is perpendicular to the disk, and it is precessing. Why? In fact, because the jet is almost in the plane of the sky. If it is precessing by 10 degrees, you see that it is changing its velocity toward the observer very quickly. And why it is so much collimated, it's because when you have an accretion disk like that, it's very highly magnetic. You have 10 to the 14 gauge side as a magnetic field. And then when it is rotating, you have these field lines which are very well collimated and are trapping the ionized gas. And you have the jet, at least the jet, not the molecules. The molecules will be dragged by the jet, but at least the ionized jet will be completely collimated. And for the precessing, you have example of this precession, but for microquasars, which are in their own galaxy. Why microquasars are very interesting is that they are solar mass scale black holes, and of course the time scale are much smaller. We have not to wait years and years to see the proper motion, but here you have SS433, which is a microquasar in our own galaxy, and you see the proper motion, they are really precessing. So we have taken example on this to make a model of this galaxy, and indeed we find that the jet can be explained by this small precession. Okay, so the conclusion that we can have a jet, and sometimes also we can have some winds, which is on the dust, which is not the same as the Eddington ratio on ionized gas, but we can have also the radiation pressure on dust. So as for the molecular tori that we have observed, I just recall you what we call the molecular torus. We call it inside the nuclear spiral. You have a system which has completely decoupled morphologically and kinematically. So we call it molecular torus. And we have several others. Here you have a galaxy with a HST, which looks almost face-on. And here you see in the molecular torus with ALMA, we have an almost edge-on torus with a lot of velocity, gradient of velocity. So this is an example. And another example here is this beautiful galaxy NGC 1365, which is a very well-known and prototypical bar spiral. You have a certain orientation, and again, a ring here at resonance. And the torus is this time seen face-on with a hole in the center. So looking at the small statistic that we had in this program, about 7 out of 8 galaxies had a molecular torus. So it's really a general phenomenon. And you see that the radius is a 10 parsec scale, with mainly the main characteristic is that the inclination of the torus is not the same as the inclination of the galaxy. Now, why? In fact, we can think of several phenomena. There is this Bardeen-Petterson effect, which is a relativistic one, which comes from below 1 parsec. You can also imagine other mechanisms like the gas arriving, which is never arriving with the same angular momentum because it's very small at 10 parsec. When you make a giant molecular cloud arriving at 100 parsec, there is no reason that it is aligned with the accretion disk. So there is several mechanisms. And we see also, like in 4258, but also in 1068, we have this measure of H2O. So at a very small scale, we see that it is also warped and precessing. So all this tend to see that this relativistic effect is doing something like modeled by Caproni, for instance. He has interpreted the precession of the jet with the Bardeen-Petterson effect. So it's possible. It's not the only explanation, but it is a possible explanation. So I will finish now with this explanation of why we do expect that the galaxy, the gas around the black hole is not aligned. In fact, we know that 4258 is not aligned. We see jets in blue, which have made a lot of trace both by H-alpha and X-ray. They have obstacle in the galaxy that they get out. We see also in the Milky Way. This is when you look near the black hole of our own galaxy. We have a ring also in HCN in orange, and then you have a mini spiral which looks almost face on, while the galaxy, of course, is a John. We are inside and we see. So we know that the center of galaxies are never aligned with their large scale, and also in 1068 is even difficult to explain, because you have at some scale 140 parsec in the top left. We have the red and blue in this sense. At 5 parsec, the red and blue has a reverse, so you have counter rotation. And then when you look at even smaller scale, 1 parsec, the water measures are even reversed. So we interpret this in saying that sometimes you accrete a molecular cloud which arrives when this direction has not the same angular momentum. So you can explain every figure, in fact. I pass this, it's exactly that. And in simulation also we see that. For instance, that the simulation of the Milky Way galaxy in the center, there are several snapshots. After a while, you have star formation, and you have some perturbation here and feedback. You have a lot of feedback due to supernovae. And after that, all this gas, by making a fountain effect, goes down. And what we see here is the gas is going in a perpendicular direction. You see a polar ring, which means that it's completely misaligned with the rest of the galaxy. And it is due to the stellar feedback, in fact. You see here face-on and edge-on, and you have some kind of polar disk, which can explain, for instance, this kind of misalignment of the spiral in the center of the galaxy. So finally, I summarize what we have learned with ALMA here. We have learned first the fueling. When you have several embedded bars, you can fuel directly the nucleus, and we have seen a lot of examples with the nuclear spiral. And the feedback, we see a lot of outflows due to AGN. When you have enough resolution, we can distinguish between AGN and stellar feedback. And finally, the most surprising thing is that there is no dusty torus, thick dusty torus, that there are thin molecular tori that are decoupled from the rest of the galaxy, and maybe by the warping and BP effect. So thank you very much.